today's class. Just where we left off yesterday, remember we were talking about, so this was lecture number 7, and yesterday the last part of lecture number 6 we were talking about the units of rate constant, right, and for a first order reaction we found that the unit of rate constant would be the inverse of time, it is either inverse of second, minutes, hours, right. If you go for a second order reaction, so it would be like this: liter, mole inverse, time inverse, making sure that whichever is having the positive exponent is written at the very first, and then you go to a zero order reaction. So, for the zero order reaction what happens is the rate is equal to k times the concentration of the reactant raised to the power 0, that means rate is equal to k. So, whatever the unit of rate is, that turns out to be the unit of k, the rate constant. We did a very quick example, and the example was that if you are given a reaction where both A and B are involved as the reactants, and it is told to you that the reaction is first order with respect to A and first order with respect to B, then can you write the rate expression? You assume the time to be in minutes. Okay. So, and this was the last thing we did yesterday, where we saw that if we have this as given according to the question, rate is equal to k times A raised to the power 1, concentration of A raised to the power 1, concentration of B raised to the power 1, then the overall order is 1 plus 1 equal to 2, and then what is the unit of rate constant? The unit of rate constant then turns out to be the unit of rate over the unit of the concentration of A times the unit of the concentration of B, and hence this is what we end up with. Now, quickly if you do if we do one more thing, which is, suppose we take another example, right, it is continuation of the same thing. We say this is example B. Okay. We have a reaction, okay, between A and B. Okay. So, these are the two reactants, and it is again said that the reaction is first order with respect to A, and okay, say second order with respect to B. Okay. So, then when you write the rate expression, so the rate expression obviously becomes like this, is equal to k, which is the rate constant, times concentration of A raised to the power 1 because it is first order, concentration of B raised to the power 2 because it is second order, hence k A B raised to the power 2, and then based on this I can write that the overall order of the reaction is 1 plus 2 equal to 3. So, now having discussed about these, it should be straightforward to you why it is 1 plus 2 equal to 3, this being the overall or total order of the reaction. Okay. Now, what about the units of rate constant? So, the units of rate constant would be then k equal to rate over concentration of B squared, right. So, I can write, what rate is? So, rate is concentration over time, here the time again you assume the time to be in minutes. So, it would be mole liter inverse minute inverse, and then I will be having, I can say mole liter, that is the unit of concentration of A, and in this case I will be having mole liter raised to the power 2. Why? Because it is second order, right. So, here now as you will realize that the first mole liter and this one cancels out, and I will be left with liter squared mole is 2 minute minus 1. So, then this would be the unit of the rate constant K. Okay. And again what you should pay attention to is that I have written liter raised to the power 2 as the first term. Why? Because here I have the positive exponent and then the negative ones come later. Hopefully now you can given a certain rate expression or given a question like this, you would be able to find out the rate expression, write the rate expression, find the total order of the reaction, and then even go ahead and find the units of the rate constant. Having looked at rate expression and also having looked at the rate constant, you must be wondering about this. What is the significance of rate and rate constant? Well, what I mean by this will soon be clear when I go ahead with this topic. Now, what happens is, because rate depends upon the concentrations, so rate will vary with the concentrations of your reactants. Okay. So, the rate will vary with the concentration of reactants. Then what it becomes is a problem when if you are trying to compare reactions. Why? Because if you change the concentration, the rate will change, right. So, what I can say is this: the rate is not of much use. Again, the rate is not of much use in quantifying reactions or comparing. Reactions, right. So, this is important because it says the rate is not of much use. Well, it makes sense, right, because the moment you change the concentration, the rate will change. Comparing reactions, the concentrations, if they differ, then again you cannot compare the rate. However, there is a way out. What is the way out? Well, the way out is, you realize now what I am trying to tell you, or what I am trying to reach at, is that the rate constant is a constant at a given temperature, right, and is independent of the concentrations of the reactants. Okay. There are a few important terms out here. So, the rate constant is a constant at a given temperature. This is important because the rate constant does depend upon temperature, the Arrhenius equation, which we will come to later, and also it is independent of the concentrations of the reactants, right. Hence, you can see, as opposed to rate can easily be used, that means the rate constant can easily be used to quantify and compare reactions. Okay. So, while rate of the reaction is in some sense useless because it depends upon the concentrations, but the rate constant at any given temperature is independent of the concentration of the reactants, and hence you can always use to quantify or compare certain reactions or compare reactions. Not only that, if you know the rate constant and the order of the reaction, you can easily write down the rate expression, right. You can easily write down the rate expression for that reaction. Okay. So, because what is rate is equal to say k times concentration of A raised to the power n, like we had done before, say rate is equal to k times concentration of A, the reactant, raised to the power n, which is the order. So, if you know the rate constant k, if you know n, then you easily write down the rate expression. So, that was in some sense the significance of the rate and the rate constant. Okay, you can understand the rate constant is fundamentally much more useful because of the fact that it is a constant independent of the concentrations, but do keep in mind it does depend upon temperature. So, if you are comparing two different reactions, you better compare them at the same temperature, because rate constant would otherwise differ. Whatever we have done up till now in when we are talking about the rates, the average rate, the instantaneous rate and all these things, we were mostly focusing on what? Drawing of tangents, right. But the drawing of tangents is not always advised, right. So, for this what we do is we go for something known as integrated rate laws, integrated rate laws or integrated rate, or I can write rate equations, okay, integrated rate equations or rate expressions, whatever. So, as I was telling you, this up till now whatever we did was to find, say suppose I would like the instantaneous rate, yeah, okay. So, suppose I am given a kinetic profile like this, okay. So, this is the concentration of A versus time t, and someone would tell me, okay, ask me find the instantaneous rate somewhere here. What I would do is I would actually then draw a tangent and then try to find out the instantaneous rate. But then the problem is that how accurately you draw the tangent will determine how accurately you figure out the instantaneous rate. That is why this is not the preferred way of doing it all the time. However, keep this in mind that if you are going to have complex reactions, which means the reactions are not straightforward or there are secondary reactions, it makes the whole reaction scheme very complicated, then obviously the way you would figure out say the instantaneous rate by drawing a tangent or the initial rate by drawing a tangent at the initial point would still be the more favorable way of calculating the rate of the reaction. But however, for reactions which are relatively straightforward, we would rather not use the tangent expression or the method of drawing the tangent and then figuring out the rate. Instead we would do something which is related to this title, the integrated rate laws or the integrated rate equations. Okay. Now, this is one of the main aspects of chemical kinetics, from where based on the integrated rate laws you can do a lot of manipulations, lot of things. But before I go to integrated rate laws, I would like to bring to your notice a very important aspect or a very important parameter in chemical kinetics, it is called half life. For a given reaction. Now, why was this concept necessary and why or in what sense is it useful? Now, again suppose you are given a kinetic profile like this, where this is the concentration of the reactant and this is the time. Okay. Now, yes, one thing is that I can go and derive the integrated rate expression and work based on that, but if I want to take a step back and based on this kinetic profile I want to say something at the preliminary level about this reaction, can I do that, and if I can, what would I base it on? What is that value, what is that term, what is that parameter that I would base my initial value or my initial focus, initial explanation, which would lead me to some deeper insights about this corresponding reaction without having to go to the integrated rate expressions. So, that is why this half life was some sort of a preliminary check based on the kinetic profile. So, that means based on this kinetic profile, as you see, can we say something about the type of the reaction that you have or you are studying. Okay. So, then this importance of half life was first coined by Wilhelm Ostwald. He was awarded the Nobel Prize in 1909. He was awarded the Nobel Prize in 1909 and he was awarded the Nobel Prize mostly for his work on catalysis and also for providing many of the fundamentals of chemical equilibrium and chemical reactions kinetics. So, Wilhelm Ostwald, so this would be L, sorry, Wilhelm Ostwald was the first person who said that half life at the preliminary level would already tell us or provide us appreciable or significant information about the reaction that we have in our hands or that we are studying. So, let us go and try to see what this concept of half life is. So, when we say when we say half life, what we mean by that is that, or we are trying to define half life, right. So, half life, this is the time. So, remember it is half life, half life is defined in terms of the time. So, this is the time it takes for the concentration of the reactant. So, again what is half life? Half life is the time it takes for the concentration of the reactant to fall to one half of its initial value. So, again what is half life? Half life is the time it takes for the concentration of the reactant to fall to one half of its initial value. Now, this is important. Okay. How do we visualize this on the graph itself or the kinetic profile itself? again as usual let us draw a kinetic profile. Okay. So, as we always say, this is the concentration of the reactant being A, and this is time, whatever unit it be, seconds, minutes, hours. Now, suppose we have a profile which goes something like this. Okay. So, this is my reaction profile or kinetic profile for a certain reaction. Okay. Now, this value, so this would be time 0 for me, so exactly the initial time. So, this value out here is my, so I can write here this is A 0. So, what is A 0? So, then A 0 is the initial value of the reactant. So, that means at the moment the reaction is starting, the value of this reactant is A 0, as 0 refers to time 0. Then by the definition of half life, if you remember, by the definition of half life, the half life would be the time it takes for the concentration of the reactant to fall to 1/2 of its initial value. So, if this is 0, this is A naught somewhere here, when this comes to half A naught, right, it is not exactly drawn to scale, but when it comes to half A naught, is half A naught, this time from here to here is called T half. Well, I will come back to this again. Now, what you can also figure from here is that if I am having half A naught, so from here to here I can again come to half of it. So, let this be, so let this be, so let me put this, okay. So, then this is 1/4 A naught, right, and I can even go and say that, okay, this is half of this gap, and I can write 1/8 A naught. Okay. So, just let me complete this, then I will explain what I am trying to achieve out here. Right. Okay. Now, let us look at this. So, let this, so let this be the corresponding intervals, time intervals, and remember I have my time axis on the x axis, the time on my x axis, right. So, now look, from A naught the half life says that is the time required to go down to half of the concentration of A naught, which is half A naught. So, this would be my T half, I can say 1, I will tell you why I am saying 1. Now, again when I reach half A naught, so then between 0 and half A naught I can again decrease the concentration by half, which will become 1/4 A naught. So, this 1/4 A naught would be my next time, right. So, from here to here, so for example from here to here you can see I can write this is T half 2, right, and again this would be T half 3. Okay. So, which I did not mention before. So, this T half is referred to as the half life, that is the symbol of half life that we always use, right. When I go from A naught to half A naught, the time it takes me to go to half of my initial concentration is T half, right. Now, we see here in red I have written T half 1. T half 1 means, again if I write here T half 1 means the first half life. Then what about T half 2? T half 2 is the second half life. What is the second half life? Second half life is the time it takes my concentration to fall from half A naught to half of half A naught, which is 1/4 A naught. So, then T half 2 is my second half life, and likewise T half 3 is my third half life, right. The concept of half life is the same. What is it? It tells you at the time it takes for me to go to half of the initial concentration of the reactant, right. So, if my initial concentration of reactant is A naught, then the time it takes for me to go to half of A naught is T half 1, which is the first half life. Why it is first half? Because A naught is the initial concentration I am starting with. Now, when I go from half A naught to half of that, so if now half A naught is my initial concentration, right, and then I am going to half of that, which is 1/4 A naught, then the time taken for that is T half 2. So, it is my second half life. Then again half of 1/4 A naught, which is 1/8 A naught, the time taken to go from 1/4 A naught to half of 1/4 A naught, which is 1/8 A naught, is my third half life T half 3. Okay. So, as you can see from this kinetic profile, you will be able to figure out based on the manner in which the concentration of the reactant is decreasing, where the first, second and third half lives would be. Generally when we say half life, we always mean the first half life, that is what we are talking about, unless and until it is specifically mentioned to you, go for the subsequent, say the second half life or the third half life and so on. The first half life is the one we generally consider, and that is what we will mostly focus on. And when I say half life, that is typically what I mean, the first half life, right. So, yes, from this kinetic profile, what we now know to do is, given the starting reactant concentration, given the manner in which it decreases, the concentration of the reactant decreases as a function of time, we will be able to figure out from this experimental curve what my half life would be. Now, what is the significance of this? Why we consider this to be a preliminary check? It would not be clear right now to you. It will only become more clear or clearer if I start discussing about the integrated rate expressions or the integrated rate laws, and then bring this concept of half life in and make the connection. But at least let me tell you this: if we consider this kinetic scheme, though it is not drawn to scale, but what you would realize qualitatively that this T half 1 is equal to T half 2 is equal to T half 3, which means that no matter at what point of this reaction you are, the half life is always the same. That means the half life is independent of the concentration of your reactant, right. So, let me write this again. What I am saying out here is, remember we said that the half life can be a preliminary check. What did I mean by that? What sort of insights can I get by looking at the way the half life is changing as a function of the progress of the reaction, right. So, what I mean is this, that if it has to be a preliminary check, I need to get something out of it. If you look at this, the T half 1 is equal to T half 2 is equal to T half 3, right. If this happens, that means the half lives are all equal. If that is the case, then what we say is, this is a unique signature of a first order reaction. Okay. is a unique signature of first order reaction. So, that means if the half lives are independent of the reactant concentration, it remains the same throughout, right, does not matter at what point of the reaction we are in. Hence, if we can figure this out, we can immediately say without doing anything else that this is a first order reaction, okay, with respect to the reactant. Hopefully, you have realized that this half life can be very important, as we said that the successive half lives, right. So, these are your, you can say these are your successive half lives which are equal to each other, being the signature of the first order equation, and as I said, it is independent of the concentration of the reactant. So, when we go and discuss about the integrated rate equation for the first order reaction, we should be able to see this again, right. Okay. Now, let us move on to the thing we started with, the integrated rate expression. So, let us start with one of the simpler ones, which is a 0 order reaction. Okay. Let us start with this. Now, this is obviously very simple. So, what we say is that as per definition of the 0 order reaction, the rate of the reaction is equal to K, if A is the reactant, K times concentration of the reactant raised to the power 0, A being the reactant. Okay. So, this anything raised to the power 0 is equal to 1, therefore, rate is equal to K, let this be equation 1. Okay. Now, also from the definition of a rate, it is very important to understand that the way the rate is defined is minus dA over d of t. Okay. This is my definition of the rate, but I am saying I am considering a reaction where A is going to P. Okay. Now, this minus d over d of t then is equal to K, let this be 2, right. Now, what we will do is we will say that, okay, then I can write this again as d of A is equal to minus K dt. So, I have two sides, two variables, one is dependent upon the concentration of A, the other one is dependent upon the variable t, which is time. Okay. So, what we will now do is we will integrate both sides, we will integrate both sides. So, which means d of A is equal to minus K d of t, and what do we integrate it between? We integrate between t is equal to 0, t is equal to 0, that means the initial time reaction is not yet started or just about to start with t is equal to t. So, this is my interval. So, for the time my initial time point is 0 and the final time point is any arbitrary time point t. Okay. Then what about the limits of the integration for A, that means the constant of the reactant. So, at time 0 I say the concentration of my reactant, which is my initial concentration, is given as A naught, not corresponding to t is equal to 0. Then as I go at time t, I can say that my concentration of A can be represented as t. So, if that is the case, then I go ahead and do the integration, keeping in mind that K is a constant, let this be equation 4, K is a constant and can be kept outside the integral, right, and can be kept outside the integral. If that is so, then immediately this what this becomes is, see I integrate this, the first one on the left hand side, it would be A t minus A at time is equal to 0 is equal to minus K, then it would be T minus 0, right. Okay. Or I can write it again as A T minus A naught, my initial reactant, is equal to minus K of T, or A T is equal to A naught minus K T. Let this be 5. Okay. So, what does this tell me? This tells me that once I have integrated my, what did I start from, my 0 order reaction with A going to P, once I have integrated that and I have set up my equations like this, then I did the integration within the defined limits, right, a definite integral within the defined time limits. For T is equal to 0, my concentration is A naught, the initial concentration. For T is equal to T, my concentration is concentration of A at time T as defined by this integral, right. And hence, when I go ahead and do the integral, I end up with an equation like this. The moment I end up with an equation like this, you soon realize, oh, this is a straight line equation, right. Does not it look like y is equal to mx plus c, right, where y is A T, c intercept is A naught, x obviously is T, and m is equal to minus k. So, y is T, c is A naught, x is T, and m actually is minus k, right. So, this is the equation of a straight line. If I want to plot a graph, how would the plot look like? So, the plot would look as you have rightly guessed. If this is A, this is time, okay. Here concentration of A at time t is equal to concentration of A naught minus K T. So, this would be a straight line. Straight line with the significance that this is my intercept, which is my initial concentration A naught, because this one corresponds to time t 0, and then the slope is equal to minus k based on my equation A T is equal to A naught minus K T. So, this is the equation I have plotted out here, right. The equation of a straight line with a negative slope. Because the slope is negative, the negative slope is equal to minus k, and from there I get k. So, I get the rate constant, okay. And one more important thing is that if for a reaction this profile is maintained, that means if plot of the concentration of A versus time t is a straight line as we see with a negative slope, then this is the signature, of a 0 order reaction, okay. So, then this is the signature of a 0 order reaction. Now, this is extremely important to keep in mind. Okay. So, you might not be given anything, you just might be given a graph plotted like this, and you might be asked what type of a reaction does it signify, and that is what you have to say, or that is what you have to keep in mind while you give the answer. So, which means again that if it is 0 order kinetics, or the reaction you are studying follows 0 order kinetics, then the plot of A versus t, that is the concentration of A at time t versus the time t, should be linear like this. And as I said again, the slope being negative by itself, this is equal to minus k, right, and hence you get k, which is a positive value, the rate constant, right, and that is why this graph is giving you. Okay. So, that was about the integrated rate expression and the plot. Plots are very useful for chemical kinetics, because as I was saying, even for a half life plot, even in a half life from a kinetic reaction profile or the plot from a 0 order reaction, you would be able to figure out what type of a reaction you are talking about. Okay. Now, let us consider the half life, right. So, let us consider the half life for a 0 order reaction. Let us consider the half life now. So, we discussed about half life before. Okay. Let me see what my initial the ending equation was. Okay. So, the ending equation was 5. So, the next equation number would be 6. I often miss or lose track of my equation numbers, but anyway, let us consider the definition of half life now, right. So, the definition was like this: if my initial concentration is A naught, then the half life, which is my first half life, and I said the half life we are going to refer to is always the first half life, is the time it takes to go to half of A naught, right. That was the interpretation, or that was the definition of half life. So, let us go back to this equation 5, where we had A of t is equal to A naught minus k t. So, this was equation 5 for me, right. So, now what happens at t half? What happens at t half, that means if this t is now t half, because I am trying to figure out the expression for half life from this rate equation, right. If I am trying to do that, what I say is that okay, at t is equal to t half, at t is equal to t half. So, this remains the same, A naught is always my initial concentration, at t is equal to t half. So, my half life, what changes is in this equation is one is t is replaced by t half, and the other thing is A gets replaced by half, that is A t gets replaced by half A naught, because that is what the definition of t half is. So, t half is what? T half is the time it takes for the concentration of the reactant to go to or to fall to half of its initial value or half of its starting value. So, you keep this as 6, once we have this, we can easily rearrange and write that k t half is equal to A naught minus half of A naught, right. And so, based on this I can go forward and write that t half or k t half is equal to half A naught, right. So, A naught minus half A naught is half A naught, and hence t half is equal to A naught by 2 k. So, this is a very important relation for the half life of a 0 order reaction. This will be 7. What does this tell you? What it tells you is the half life is directly dependent upon the concentration of the reactant. So, greater the concentration of the reactant, greater the half life. Now, why do I say it is only dependent on the concentration of the reactant? Well, it does depend upon K, but do realize that for a given reaction K at a certain temperature is constant and 2 is obviously a constant, right. So, essentially what I mean to say is essentially it is depending upon the concentration of A naught. So, this is what we can write: the half life for a 0 order reaction is proportional to the concentration of the reactant, right, is proportional to the concentration of the reactant. So, that means higher the concentration, higher the half life, lesser the concentration, lesser the half life, right. That means again based on this, higher concentration means higher half life. Okay. In other words, as a reaction proceeds and if that reaction is of 0 order, here we are talking about a 0 order reaction right now, because everything is under the description of a 0 order reaction. So, as a reaction proceeds and if it is following 0 order, then the half life also decreases, then the half life also decreases, right, which makes sense again, because what happens as the reaction proceeds? What happens as the reaction proceeds is that my concentration of the reactant is decreasing, right. Now, you can take A naught, you can take this A naught like A naught going to half A naught, right. At half A naught what has happened is it is already less than A naught, right. Now, if you go from half A naught to 1/4 A naught, see what is happening is you are decreasing it even more. Half A naught is less than A naught, 1/4 A naught is even lesser than half of A naught, right. So, what it means is if you are going to calculate T half, right, then T half, the first half life would be having the maximum value. When you go to T half 2, which is the second half life, which is the time it takes for you to go from half of A naught to 1/4 A naught, because the concentration has decreased from A naught to half of A naught, the half life will also decrease, okay, and so on. And hence, as the reaction proceeds, the concentration of the reactant decreases and so does the half life. This is very characteristic feature of a 0 order reaction. Now, recall our concept of half life being used as a preliminary check, okay, and this is what was meant. So, what was meant was that for the 0 order reaction, if it is a 0 order reaction, then as the reaction proceeds, the half life decreases. If you have, so now conversely, if you are given a reaction profile, right, if you are given a kinetic profile and from there you are seeing that the half life is decreasing as a function of time, that means as the reaction is progressing, then you immediately say that as a preliminary check, because the half life is decreasing as the reaction is proceeding, it means that it should correspond to a 0 order reaction, or that the reaction I am looking at follows 0 order kinetics, right. Hopefully now, having discussed half life before we started this integrated rate laws or integrated rate equations, that time I was telling you that half life can be used as a preliminary check. Then we moved on to the 0 order, integrated it out, got this linear dependence of the concentration on time, negative slope. From the slope you get minus k, and hence you get k being a positive quantity, but then you see half life, it decreases as the reaction is progressing, and then it tells you as again a preliminary check. I am using this word each and every time, having not done anything else, just using the half life you are able to tell that this reaction must follow 0 order kinetics. Okay. So, you can see that today in this class we have entered this realm of integrated rate laws or integrated rate equations. We are done with the 0 order rate equation. So, what we will do is in the next class we will focus on the first order and second order rate equations, and then again move on from there and discuss the other aspects of chemical kinetics. Okay. Thank you.